everyone. We are going to talk today about 6.4, which are areas in the xy plane now. So in 6.3, we saw that if f of x was positive, right? So a couple things with f of x. It had to be continuous, and it had to be positive. And if it was all those things, right, then if I had this function, this was in 6.3, above the x-axis somewhere, here's my f of x, right? We have this new definition now that if I integrate, take the definite integral from a to b, so if I take that definite integral, right, oh, those lines, pretend that they're straight. This gives me the area. So a to b, f of x dx. In the end of that section, we talked about this idea of Riemann's sums, where really, how is this area really found? It really was found by estimating the area of this guy with these rectangles, right? Don't mind these things that are not rectangles. I'm doing right-hand endpoints here. So I have these rectangles that estimate the area. And when f of x is positive, what we found was that the height of each of these rectangles, like this guy right here, was just my function evaluated at one of those endpoints of the subintervals, okay? So the question today is, well, what if my function is not positive, right? What if it is not non-negative? What if I have a function and I want to integrate, and let's say my function does something like this, and I want to integrate from a to b, so maybe I'll put a kind of in the same spot here, and we'll put b up here. Okay, so what if I did integrate from, well, I guess a is getting moved over a little bit. If I did want to integrate from a to b, what would actually happen here? What would the integral from a to b give me now that f of x is not positive? Or non-negative, same thing. Well, it's not the same thing, but for all purposes, it's the same thing. So as you saw in the book, what ends up happening is this actually gives me a signed area, signed as in S-I-G-N-E-D. So when I look at maybe taking, if I took this number line here between A and B and I broke it up into subintervals, and I did this idea of estimating this area using some rectangles, right, which you did in the last section. Okay, so I'm doing left-hand endpoints here. This guy is at 0. Well, look, so this is my rectangle here. Look at what would happen here. So I'm looking at this subinterval right here. Again, what do? We grab the function, right, to determine the height of my rectangle. So if you notice here, look at what happens. Let me finish this off really quick. I love the shift button here. Careful how you say that. Left-hand endpoint here would be 0, and then I would come up here and I'm just getting these rectangles, right? So I would color in all of these rectangles, and that is what the definite integral, that's one way of interpreting the definite integral and what it gives us. The thing is, though, when you actually evaluate the function at these endpoints, look at what's going to happen here. When I take, if this is x1, this is fine, x2, x3, x4, notice that f of x4 is negative. Your y values are below the x-axis. This guy is less than 0. So what you're going to end up getting is you're going to end up getting a rectangle that basically has negative area. Now I know that sounds silly, we can't have negative area, but the idea here is that that implies that that rectangle lies below the x-axis, okay? So when you're looking at that definition that you wanted to write down in your book, I won't write it down here because you can write it in your book, that if we just take the integral from a to b, it's basically the area above. So this guy right here equals, one second, let me undo that. This guy right here equals the area above the x-axis, okay, minus the area below. So if I actually want the exact area between the x-axis and the graph itself, I would have to break this up. So if I actually wanted this area here, this area here and this area here, I would have to do 3 different intervals. So I would have to integrate, you know, this part, this would be one integral. I would have to integrate this integral right here. I would take the absolute value of it because this guy below the x-axis is going to give me a negative. And then I would have to add it to this integral right here, which we know we can do from the properties of integrals. So I hope that makes sense. The definition is in your book. You're welcome to, you should copy that definition into your notes. But what I really want to do is just show you some examples on how we would even do this. Okay, so the first example I want to give you, and in this section it's going to be very, helpful for you to have a graphing calculator and you're really going to probably need a graphing calculator for the exam. Okay, no TI 89 calculators, so make sure you have an 84 or an 83, or you can borrow a graphing calculator from someone. And if you need help with how to graph on that calculator, please just let me know. So let's do some examples. The total area, okay, between the x-axis and the graph of the function. So let's look at the function f of x equals, what do I have here? X squared minus 3x over the following intervals. So I want a couple, we want to do a couple intervals here. All right, so the first interval, my English isn't super great there. I want to look at x equals 0 to x equals 3. Okay, so I want to look at what is the graph. First, I need to know what the graph of this function looks like, because I need to know, is this function above or below the x-axis? That's going to be a big thing when you do these. You want to look at what is this function, where is this function, above the x-axis or below the x-axis? So if you look at this, remember this is a parabola. One way to graph these if you don't have a graphing calculator is to look at the zeros, right? Where is this guy equal to 0? When x is 0 and when x is 3. So I'm going to graph this guy. I'll probably just use this graph for the remainder of the problems. So if I put in 0, right, so here, what are my zeros? 0 and 3. So I know that my graph crosses at 0. This isn't going to be perfect, but what in life is 0 and 3. And let's do a different color so you can see it. 0 and 3. This is a parabola opening upward, right, because the x squared has a positive. And then let's just plug in some values. So just to kind of see what we have here. When x is 1, what is f of 1? All right, that'd be 1 minus 3, which is a negative 2. So I know I'm going to be down at negative 2 when f is 1. Let's kind of extend that guy down. Oh, that didn't work. Whoops. Extend that down a little bit. So when f is 1, we're at negative 2. Okay, and I think when you put in 2, we're also going to be at negative 2. You know, with the parabola, it has that symmetry. But let's just check when we put in 2, what is f of 2? Well, we get 4 minus 6, yeah, negative 2. So I'm going to also be at negative 2 here. So this is a parabola opening up, and we're just going, these are some of my points. The vertex is probably going to be, you know, right about here. It doesn't have to be perfect. I just want to be able to get an idea of what this graph looks like. And why do I even care about what this graph looks like? Well, I care because I want to know what is above and below the x-axis. But that's really all I care about. Let me erase some of this here. That's going to bother me. There we go. That parabola is not perfect, but you're used to me now. So, all right, so from 0 to 3, if I actually want to find the area, what do you notice about the area between 0 and 3? So this is A. We'll do this as the yellow part. We know that this yellow part right here is below the x-axis. So when I draw those rectangles are going to have a negative height. So when I actually take the integral of this and I want to find the area, I just need to take the absolute value. So the area of this is going to be the absolute value of the integral from 0 to 3 of x squared minus 3x dx. Absolute value. Okay? So we'll take the antiderivative, which is 1/3, again, absolute value, minus, 1/3 x cubed, don't forget that x cubed, that would be good, minus 3/2 x squared, absolute value, whoops, we need a, This gets a little crazy with the evaluation. 0 to 3, absolute value. Also, you know, if you decide to take the integral and then take the absolute value afterward, that would be fine too. I will understand what you mean by that. So when I plug this in, if I plug in 3, I get 27, right? Divided by 3, which I believe is 9. And then minus 27 over 2. So if you take 9 minus 27 over 2, I believe you get a negative 9 halves. So the absolute value of a negative 9 halves is a positive 9 halves. So again, look at what this gives you. I just want to point out that in the absolute value, you get a negative 9 halves. And why is that negative? Because it's below the x-axis. So our answer for part A is going to be a positive 9 halves because I want to have just the area. Okay. Remember, does it make sense to have a negative? Yeah, sometimes it does. Now, when we're talking about area, it might not make sense. But when we're talking about remember what the definite integral also gives us. It gives us net change of a function. So if I was worried about the net change of the antiderivative of this between 0 and 3, I want to put absolute values because I want to know, is my net change decreasing or is it increasing? Okay. But when we're talking about area again, I want positive. Okay, so I want to continue with this example. Let me just add a new layer really quick. Maybe. Maybe not. My computer's kind of slow. It's thinking very hard about adding a new layer. Sorry about this. I may have... Oh no. The circle of death there. I may have killed it. Anyway, we'll add another layer here in a moment, possibly, which would be great. Okay, so I bet that looked a little weird. My program died on me, so I lost everything I'd written, but that's okay. I just rewrote kind of what we were just talking about. And remember we had, well, you remember because it was probably seamless for you. We found that the area of this yellow part of this function between the graph and the x-axis was 9 halves. So I want to do another example here. I would like to do, what if I still want you to find the area between this graph right here and the x-axis, but instead of 0 to 3, I want you to find x equals 0 to x equals 4. So now, let's bring in another color here. So now, not only do I want the yellow, but I also want, you know, if this graph continued up, which it does, obviously, I'm going to just move it over a little bit so it's easier to see. I want you to go from 0, and then also I want this area right here. So I think it's pretty easy to see that we're just going to have two separate integrals, okay? I need to look at the integral from 0 to 3 because that's where the graph is below the x-axis, and then I'm going to add the area of the integral from 3 to 4 because that is where it's above the x-axis. Because again, if I just integrate from 0 to 4, it's going to take this negative area plus this positive area and put it together, which is not what we want. So my area then will be the integral from 0 to 3, which we've already done, so that's kind of nice, minus 3x dx, plus the integral from 3 to 4 of x squared minus 3x dx. Now the one thing that I do need is I need these absolute values right here because I know this guy here is negative. Now of course we already have that figured out, so we're going to go ahead and put that 9 halves in. Here I don't need absolute values because I know that it's going to be positive, so I have 1/3 x cubed minus 3 halves x squared, and I'm going to evaluate this guy from 3 to 4. I'm just going to do that in my calculator really quick. Not that I can't do that in my head, but I don't know, you know. I do have a calculator, so so I get like 64/3 minus 24. And then minus, when I plug in that 3, we get 9 minus 27 halves, making sure to put parentheses, of course, around all of this. So what I get for that is I get 11/6. So I get 9 halves plus 11/6. And if we just get a common denominator, we get 19/3. Good. You should check me on that. That's probably shouldn't be like in stone. But that's the blue part here. So if I wanted this blue part, that's going to be that plus now the yellow part. So that is the area that I am going to get that 19/3. I hope that makes sense. Okay. And then, you know, the last one, we'll just set this one up and then I'll let you finish it. What if we wanted x equals -2 to x equals 3? So again, we get kind of the same thing where I have some of this that is above the x-axis and some of it that is below. So now I want this area right here. So this is going to be part C. And then I want, again, all of this until 3. And so how would we set this up? Well, now my area, I'm going to integrate from -2 to 0, right? Because that's where I have this positive area right here of my function, x squared minus 3x dx, and then plus that area that we've already been doing. So that's 0 to 3, and of course absolute values, x squared minus 3x dx with the absolute value on the end. And I'll let you finish that one as an exercise. You can do that one. But I hope that makes sense how we kind of work with that. Good. I want to do a couple more examples from this section and then I'll let you go. But the other thing in this section that is quite important is the area between two curves. So you should have this in your notes, but if I want the area between two graphs, okay? So let's just say f of x and g of x. What you could find when you've read in the book is, what do we do with these? We just subtract. Isn't that great? Love it. Now, what do I need to know here? One quick thing here, and when you write this down in your notes, you know, with the like beautiful definition and everything, this is for f of x being bigger than g of x on that interval, okay, on the interval a to b. So we got to make sure we know which function is larger, because I'm going to be taking, you know, the top function minus the bottom function. And you can kind of see why this is true. We can just do a quick little sketch, okay? So if this is my function f, and this is my function g, and g does not have to be positive. I'm just putting it in the first quadrant. Look at what would happen if I took one of those, whoops, if I took one of those little little rectangles, right? Those cute little rectangles that we're using to estimate area from now on. If I wanted to find the height of this rectangle, and let's say I just use the height to be between here and here, what is this distance? Well, that distance would be f of x minus g of x. That's how we find distance, right? We take the difference between two things. So let me show you. I want to do an example. Well, you know, we're at 17 minutes already. I just want to do 2 examples here. So let's find the area between the graphs of, so let's let f of x equal, have f of x equal x squared minus x and g of x equal 2x over the interval. So this is what's important. I'm not just saying it's the area bounded by these two functions. I want the area actually over this interval that I'm going to give you. And the interval I'm going to give you is -2 to 3. Okay, so first off, again, we need to graph these functions. So if you have a graphing calculator, those graphing calculators are going to be worth their, you know, $100 or I don't know, maybe you wouldn't agree, but they're going to be worth their money here for a while in this class. So I'm going to graph this. So x squared minus x is kind of like the one we had before. It looks like, you know, if I factor this guy, x times x minus 1, my zeros occur at 0 and 1. And then we sure know, of course, what 2x looks like. But I'm going to -2, so I want to give myself a little bit of room here to be able to graph this. So I'm going to make my tick marks a little smaller. Because we're going up to 3. So I need to be up at 6 because I know when I plug in 3 for 2, I'm going to be up at 6. So let's look at what this looks like. So x squared minus x, I know it goes through 0 at 0, and it goes through 1, right? at 0. So it's going to do something like this. Now, one thing that you're going to want to do is you're going to want to see where do these two meet, if they meet at all. So one way to do that is I'm going to set them equal to each other. So if I set these guys equal to each other, what that tells me then is where these two graphs meet. So if I bring the 2x over, I get x squared minus 3x equals 0. So factor an x out, and I get x times x minus 3. So I know when x is 0 and when x is 3, these guys meet. So I'm going to go ahead and graph, because I know the line 2x is a little bit easier to graph. I'm going to graph this line 2x, which I know at 3 goes through 6. I know that that's not perfect, but, and then I also know, well, clearly that's not perfect at all, but it's going to go through 0. So what's nice about this is now I also know this parabola comes up like this, right? It goes through 0, 0, and then I know it must, oh man, this is going to be tough for me. It must come up, oh my goodness. Oh, I'm sorry. I wish they had like a parabola thing. I'm going to just do this maybe fast. Come up, and they meet right there. So I'm sorry about that. Maybe not. Next time I have to do all these graphs, I'll make you a picture. Man, I got to try one more try at that. I hope your graphs, when you do your notes, are much better than mine. I promise when I graph on the board, it's not as bad. But this is the area that I want to find, right? Now from -2 though to 3. So this is why this one is a bit interesting, because I want to go from, now remember, this graph goes all the way up, this parabola keeps going up, right? So what do I want? I want the area between -2, so -2 right here. Okay, so I want this area right here between the graphs, and then from all the way to 3. Okay, so that's the area I want. Now the interesting thing about this, and why I wanted to do this problem for you, is that I actually have to have two separate integrals, because in this case over here with this first yellow area, this guy right here, which one is bigger than the other? Well, the parabola is on top, right? So I'm going to have f of x minus g of x on this side. But on this side, what do you notice? This line right here, that's the one that is larger than the other one. So I'm actually going to have g of x minus f of x on this side. So I'm going to set up this, I'm going to set up these definite integrals for you, and then I'm going to let you go ahead and evaluate these integrals, because some of the, I'm going to get rid of this so I have some room. Some of the hardest part about this is just actually being able to set up the integrals. By now, you should feel good about taking the definite integral. If you don't feel good about taking the definite integral, I need you to let me know, and we need to get you some practice on that. So again, what is my area going to be? I'm going to go from -2 to 0. Okay, -2 to 0. Which graph is on top? It's this parabola, if you can see that. So I would have x squared minus x minus 2x, okay, dx. And I'll get you a little bit further than that, but that's the first area. And then my second area, I'm going to do plus 0 to, what do I want to go to? 3. And now look what's on top here is the line. So I would have 2x minus, please make sure you put parentheses here. You are subtracting more than one term. So you must put parentheses and take that negative through. And then, you know, before you actually do this, why don't you go ahead and simplify these guys a little bit. -2 to 0. I can combine some like terms. Make your life easy. Simplify before you take antiderivatives. There's less error then, or chances for you to have error. And then here, this, I like to put my squared terms first. You don't have to, but I like to. You know, we just are going to get the opposite signs, because all we did was switch the order of subtraction. So I'll let you do these two integrals. Those should not be hard for you to do, especially because we're almost at 25 minutes. And I want to do one more example for you, and then we'll call it good. So I hope that makes sense. That's an important one to understand, that the graphs switch which one is bigger than the other one over the interval we're looking at. So you need to have two separate integrals. All right, let's look at this. Let's look at one more example. Oops, let me clear this one. Okay, one more example and then we'll call it good. All right, so my next example, I want you to find the area of the region bounded by the functions. And this one is almost a little bit easier than the one we did before. But of the functions, f of x equals 5 minus x squared. And, I mean, it might not look like it, but let me show you why. We're not going to have two separate integrals. G of x equals 2 minus 2x. Okay, so that's all the instructions say. Find the area of the region bounded by the functions f of x equals 5 minus x squared and g of x equals 2 minus 2x. So let's think about what these graphs look like. This is a parabola facing down, right, because of that negative, and it's shifted up 5 units. So it's important to know that stuff from like college algebra. What is this guy here? This guy is a line with y-intercept 2 and slope -2. But one thing that helps me when I do this is finding where they intersect. If they intersect, they might not. But if they give you a question like this where they do not tell you an interval over which you're looking at x, then that really means that these guys are going to intersect. So I'm going to set these equal to each other. I'm going to move everything to the right-hand side because I want my x squared term to be positive. So I have minus 2x, and then when I subtract that 5, I get minus 3. You are in Business Calc 2. There are no excuses for you to not be able to factor. If you don't know how to factor, I need you to let me know, or you need to look up some videos about it, because that is something I am assuming you can do. So look at what we know. We know that when x is 3 and when x is -1, that is when these two functions are going to meet. So let's do this. 3 and -1. So let's look at g of x first, because I think g of x might be a little bit easier because it's a line, right, to plug these things in. So let's put some 3 and -1. Okay. Get some nice tick marks going. I know I got to be up at 5 at least because this guy's shifted up by 5. So let's look at 2 minus 2x. So I can just graph this if I want to. So I can go up to 2, right? I know I go through 2. And then what is my slope? -2. So I'm going to come down 2 over 1. Or I can just put in 3. If we put in 3, we get 2 minus 6, which is a -4. And so I know that I'm going to be down here at -4. If I put in -1, I'm going to be at 2 plus 2, so I'm going to actually be at a +4. So this is going to be my line. Okay, that's going to be g of x. And the nice thing is about graphing that line, I know that at this point right here and at this point right here, when x is -1 and when x is 3, I'm going to meet with this parabola. I know when x is 0, the parabola is at 5, so my parabola, and I know it's a parabola opening down, so my parabola must do something like this. Oh my goodness, you guys. I'm so excited. That's like the best parabola I've ever actually drawn for you. I'm going to get rid of these little arrows. Wow. It's not even that good, but I'm going to be pretty excited about that. So what's nice about this is I can see that the area of the area that I want to find, right? This is the area that I want to find right here. So a lot of this was just algebra. I haven't even done any calculus yet. So if you need to, get your graphing skills up, you need to maybe, if you need some examples that can help you, or you need to, YouTube some videos on how to graph some of these things. And the nice thing is, because we put up the work up front here, I know that when I find this area, what am I going to integrate from? I'm going to integrate from -1 to 3. I know that's going to be true because that's where these two meet. Which function is larger? Well, if I drew, one way to determine that is if you took, I usually will just draw like a tiny little rectangle here. If I drew this rectangle, right, the top of my rectangle lies on the larger function. So what is the larger function? That's the parabola. So that would be 5 minus x squared. And then I'm going to subtract the smaller function, which is g of x, dx. And now we might as well do this one. kind of miss doing these. So what do we get? Negative 1 to 3. I'm going to simplify here. Put my x squared term first. This x term becomes a positive 2x. And then 5 minus 2 is a positive 3 dx. Okay? Take the antiderivative. I get a negative 1/3 x cubed plus x squared plus 3x, all evaluated from negative 1 to 3. All right, let's plug some numbers in. If I put in 3, I get a negative 27/3, which is 9. I guess we could just write 9, negative 9. Negative 9 plus 3 squared, which is 9. That's great. Plus 3 times 3, which is 9. Oh my goodness. Minus, let's put in the negative 1. Remember, when you cube a negative, it stays negative. So that actually becomes a positive 1/3. When you square a negative, it becomes positive. And then minus 3. So those guys are gone. Oh, what do I have? I have 9 minus 1, which is 8, plus 3 if I change the signs, which is 11. And 11 minus 1/3, I think, is 32/3. You should check me, because me doing arithmetic on my own is not always the best thing. I hope that makes sense. I know that was a long video, but I wanted to show you enough examples of these so that you felt comfortable doing them. So go do your homework. Make sure you do your suggested problems. Make sure you look at the fun sheet so that you have lots of practice on how to do these and that you have lots of examples of different functions you can do. All right, you guys. See you soon.